So, uh, we have seen that if f is a continuous function from a b to r continuous, then f is bounded. Now, the question is that in this case one can ask that whether, so that means what? That means supremum of f of x, x belongs to a b, this is equal to m, which is finite. That is what is the meaning of this statement. Now, one would like to ask that does there exist a C belongs to a b such that f of C is equal to m, this is or C or x naught, whatever I can write, x naught is equal to m. As a matter of fact, the answer is yes. So, we can, so I can write it as a theorem if f from a b to r continuous, then there exists x naught and y naught such that supremum of f of x, x belongs to a b is equal to f of x naught, and infimum of f of x, x belongs to a b, this is equal to f of y naught. The proof is let suppose not, then f of x is strictly less than m for all x belongs to a b. Now, define g of x, which is equal to m minus of f of x. As you can see that g is a continuous function, because f is a continuous function, m is constant. So, this is continuous. Not only that, this is strictly positive. So, we can talk of 1 by g x, and this is also continuous. By the previous theorem, what we have seen is that 1 by g x is a function, 1 by g is a function from closed interval a b to r, therefore, it is going to be bounded. So, there exists a C such that 1 by g x is less than or equal to C. This will imply that g x is greater or equal to 1 by C. This will imply that m minus of f of x is greater than 1 by C. This will greater or equal to, that means f of x is less or equal to m minus 1 by C, and this 1 by C is strictly positive. Now, here if this is true for all x, now m minus 1 by C, 1 by C is a positive number, m minus of 1 by C is strictly less than m. But what is m? M is the least upper bound. So, now here is a number which is smaller than m, and f of x is less or equal to that number. So, m cannot be a least upper bound. Therefore, this is a contradiction. So, there exists a x naught such that f of x naught is equal to m. Similarly, we can prove it for the infimum. So, once we have these two, so even if you are having some problem with the proofs, do not worry about that, but the fact is important that if f is a continuous function on closed interval a b to r, then f is bounded. It says that not only it is bounded, the bound is going to bound will be attended, in the sense that there will always be a point in a b such that f of x, f of that point is going to be the supremum of f of x, and another point for which f of that point is going to be the infimum of f of x. Okay, so, now this is what we are saying is that that is the maximum value which is going to f is going to have. It can happen something, our f can be like this. Now, you see this value, this may not be the maximum value of f, but if suppose this is a point x naught, if I look at an interval, in this interval this is having a peak, this is, if I look at a small interval, then in that interval this is the maximum value it is taking. Similarly, around this point I can find an interval, in that entire interval f is going to take the minimum value, is attending the minimum value here. In comparison, so here, and suppose in this interval it is going to be. So, what we want to say is that, look, in small portion we can see that where f is attending maximum or minimum value. That led us to the definition of local maximum and local minimum. Let I an interval okay, and we say that f has a local maximum at x naught if there exists a delta greater than 0 such that f of x naught is greater or equal to f of y for all y belongs to x naught minus delta to x naught plus delta intersection of I. Similarly, we can say that f has a local minimum at x naught if there exists again a delta such that is less or equal to f of y for all y So, like this point it has a local maximum, at this point it has a local minimum. So, now how we would like to see that what are the condition on f which will tell us that which point it is going to have a local maximum or a local minimum. So, this is what the derivative comes to our help. Let f from a b to r, suppose f has either a local maximum or a local minimum at a point C belongs to A B. Now, if f is differentiable at C, then f prime of C is equal to 0. Let us look at this. So, now this at this point, let us say f is differentiable. Now, f prime at this point, f the tangent at this point is going to be parallel to the x axis. Similarly, this is happening at this point, this is what it is happening. So, now the proof is not hard at all. Suppose f has a local maximum. At C. So, there is a delta by definition of local maximum such that f of x is lesser equal to f of C for all x belongs to C minus delta, C plus delta intersection of I. I can choose my delta now to be so small that C minus delta to C plus delta is going to be inside I if C is not. So, I will take this C is here, because when I am talking about the differentiability means I will need some space of C minus h to C plus h. So, this is true. Now, for h greater than 0, f of C plus h minus of f of C, then definitely this is going to be a negative number, and divided by h is positive, this is a negative number. Now, if h is less than 0, f of C plus h minus of f of C, this is again a negative number, because f of C is greater or equal to, for small h, divided by. Therefore, you can take this as small h. So, we know that f is differentiable at C. Therefore, I can take the limit h goes to 0 plus, that is going to be the limit of h goes to 0, that is going to be f prime C. So, f prime of C, which is equal to limit of h goes to 0 plus f of C plus h minus of f of C divided by h, this is going to be less or equal. Similarly, from this we will get similarly f prime of C which is greater or equal to 0. Now, f prime of c is less or equal to 0, f prime of c is greater or equal to 0, both this thing will imply that f prime of c is equal to 0. Remember what it is saying. It is saying that if it attains a local maximum or local minimum, then and f is differentiable at that point, then f prime of c is equal to 0. So, let us uh, introduce some terminology definition. We say that f has a local extrema at C if either f has a local maximum at C or has local minimum Now, the point in this case we say C to be a critical point. Now, what our result is saying is that suppose C is a critical point and f is differentiable at C, then f prime of C is equal to 0. It is converse is not true. If f prime of x is equal to 0, then not necessarily mean that C is going to be a critical point of f. Converse of the result is not true. Take for example, f of x is equal to x cube. Now, f prime at 0, which is equal to 3 x square and this is equal to 0, but as you can see this is what is the this is x square x cube this, and at this point at the origin this is not a, neither it is a local maximum or local minimum. You can always find some, any neighborhood if you take, you can find some point which is bigger than 0 and some point for which f is less than 0. So, 0 is not a critical point for f of x equal to x cube, however, f prime of 0 is equal to 0. So, converse of this theorem is not true, and also the previous theorem, what we can say is that it is not valid for the end point, because at the end point we have a technical issue of defining the derivative. So, now it is, so what we are saying, I mean if f is differentiable, it has a local maximum or local minimum, then we are going to get a tangent at that point which will be parallel to x axis, or f prime of c is equal to 0. Now, the question is that when can we ensure that f prime of c is equal to 0? So, this is what is one of the most important theorem of calculus, which is called Rolle's theorem. What does it say? Let f from A B to R satisfies 1, f is continuous on A B, f is differentiable on A B, and thirdly f of A is equal to f of B, then there exists, this is the symbol for there exists, I will be using this symbol throughout this course, a C belongs to A B such that f prime of C is equal to 0. So, what is it saying? Suppose I have a function which is continuous and differentiable on A B, and f of A is equal to f of B, and this is what the function is. Then there will always exist at least one point in which f prime of C is going to be equal to 0, that is what it is saying. Okay, so let us look at the proof of this. So, if f is constant, like f of A is equal to f of B, which is equal to f of x, then clearly f prime of x is equal to 0. So, all points they are going to be f prime of x is going to be equal to 0. Now, f is not constant, then f not constant. So, there will be there exists a x in A B such that f of x is not equal to f of A. Now, f of x can be bigger than f of A or f of x can be less than f of A. Let us assume that f of x is bigger than f of A. Let f of x is strictly bigger than f of A. Similarly, we can argue if f of x is less than f of A. Then, now f is a continuous function on A B. Therefore, it is going to be bounded, and not only bounded, it is going to attain the maximum. So, therefore, there exists a C such that, and then the C is going to be inside the open interval A B, because f of x is a candidate, the x what you have got, and there will be many more. So, definitely that is going to be bigger than f of A such that f of C is maximum. Now, what we have proved in the previous theorem. So, this C where it is being attained the maximum, definitely this is going to have, it is going to be a critical point. Maximum means it is going to be also local maximum, local extrema will also be attained there, and f is differentiable at C, because f is differentiable in the open interval A B. So, this will imply by previous theorem f prime of C is equal to 0. That is what the Rolle's theorem is saying about it. And let us see some very beautiful applications of the Rolle's theorem. So, the important thing in the Rolle's theorem is that it has to be continuous on the closed interval A B, and it has to be differentiable on open interval a b, and f of a is equal to f of b. So, now just see a practical thing that suppose a object is moving from one place to another. Now, when it is same at two points. So, you take a point here, an object is moving, you want to draw the motion of this object whatever way. So, after some time it comes back to the same position. This is the time, this is position. So, after this, after some time, that means, so somewhere in between these 2 points, 2 time, there will be a time where the velocity is going to be 0, because f prime of by Rolle's theorem is saying that there will be a point C somewhere in between open interval a b, where f prime of C is going to be 0, that means velocity is going to be 0. Suppose if you throw something, then it is going to be there and then it comes back to the same position, then obviously at some point of time the velocity is going to be 0. And some other application is that now let us look at the equation x to the power 13 plus 7 x q minus 5 is equal to 0. So, one would like to ask that whether it has a real 0 or not. So, by intermediate value property, obviously, if you look at that f of 0 is equal to minus of 5, which is less than 0. Now, f of 1 which is equal to 8 minus 5 3, which is positive. So, by intermediate value property says that it has a real root, it has at least one real root. Now, the question is that can it have two real roots? So, now if there are two real roots, so there exists a x naught belongs to 0 1 such that f of x naught is equal to 0, at least 1 by IVP. Now, suppose x 1 belongs to R such that f of x 1 is equal to 0. Now, this x 1 can be, if this is your x naught, can be bigger than 0 or it is less than 0. So, now you look at, so obviously, f of x naught is equal to 0, f of x 1 is equal to 0. So, there exists by Rolle's theorem there exists a y naught belongs to x naught x 1 such that f prime of y naught is equal to 0. Now, let us look at the f. If this is our f of x, then f prime of x is equal to 13 x square plus 21 13 x 12 plus 21 x square, which is equal to x square 13 x to the power 10 plus 21. So, this is equal to 0, that what it shows is that x has to be equal to 0. So, x is equal to 0. So, now what we can safely say is that there cannot be any. So, for this there is exactly one positive, rather what we can say is that for this exactly one positive real root. Now, as you can see that if x is negative, then f of x, if x negative, then f of x is strictly less than 0. So, there is no real root on the negative axis, and what you are showing is that there is exactly one real root in the positive axis. So, this function cannot have more than one root, real root. So, without even factorizing, we could get this. So, that what intermediate value property will tell many times that there exist real roots, but on many occasion we can use Rolle's theorem to say something more precise. We can be more precise to say about how many roots some of this polynomial have. Okay, thank you. So, we will continue with uh, the Rolle's theorem and ask ourselves what can be the generalization of this theorem.